So we're going to start on page 1. Okay. And you'll actually find that the first section, 3.1, 3.1a, b, and c are all review of things we've already done. Okay. So have we talked about electrolytes already?
Yeah.
Yes, we're going to talk about them a little bit more today, just to kind of give you, a little review plus a couple more extras. And have we talked about ionic and molecular solutions?
Yeah.
A little, right? And have we talked about precipitation reactions?
Yeah.
Yes. So that's what's going to be your homework for the weekend is 3.1a, 3.1b, and 3.1c. You don't have to do every single question, just enough so that you feel good about it. Yes, because they are all review. Yes, of course. So 3.1a, electrolytes. Electrolytes are found in, as everyone wants to tell me, Gatorade. They are found in your body. They are found in seawater, in batteries, in plants, and all kinds of other places. By the way, if you don't like the staple on the booklet, you can always unstaple it and stick it in a binder. Or if you need a duotang, I can probably find you a duotang. The next unit will be properly bound because they fixed the binding machine. I am so excited. This is awesome news. Okay? Anyway, what is an electrolyte? What does an electrolyte do? Conducts electricity. And it conducts electricity in
aqueous solutions.
In aqueous solutions, or in any solutions really, but we'll just say in solution. Okay? And what has to be present in order for it to conduct electricity in solution? Charges. And what kind of particles provide the charges in solution? That charges. And in this case, yes, it is ions. So, an electrolyte, a substance that conducts electricity due to the presence of freely moving ions, because current electricity is the movement of charged particles. So you need to have charges that can move. Now let's say that we have here a copper wire. A copper wire does not contain freely moving ions, but metals, their valence electrons are able to hop from one atom to the other. So in a wire, the electrons are the mobile. Do you guys know the word mobile? Mobile just means able to move charges. Now, the reason they have mobile charges is because metals have mobile electrons. Solutions are not metals. Are solutions made of metal? No. So do they have freely moving electrons? No. So we can't have moving electrons in solution, so we do have freely moving ions when it is in solution, okay? Not electrons in solution. So let's take a look at this little picture down here. Can you think what that black thing is? That's a battery. And you'll notice it has a positive terminal and a negative terminal. Do the electrons move towards the positive terminal or the negative terminal? Positive. Why? Because opposite charges attract. So the electrons move that away. And they move away from the negative terminal for the same reason. Well, the opposite reason. What do opposite charges do? They repel. Oh, same charges repel. I'm sorry. That was what I meant to say, and it just did not come out that way at all. It came out the completely wrong way. So like charges repel, opposite charges attract. That's what I meant to say. Okay. Now, as the electrons move into this piece of metal, and we call that piece of metal an electrode, what charge does that electrode take on as the electrons move in there? It becomes negative. So we have negative, negative, negative. And as the electrons leave the piece of metal on the right, which is our other, what was that word? Electrode. As the electrons leave, what charge is left behind? Positive. Yes? So the electrode on the left is negative, the electron on the right is positive. Which direction do the cations move? Do they move towards the negative electrode or the positive electrode? Towards the negative electrode, because opposite charges attract. So the cations move towards this electrode, which is called the cathode. Why do you think it's called the cathode? Because it attracts the cations. The cations move towards the cathode. Which direction do the anions move? They move towards the positive electrode. So what do you think we call that electrode? We call it the anode. Yes? So anions move towards the anode. Now, I'll be honest with you. For this unit, you don't need to know the words anode and cathode. And you don't need to know how this whole thing works. But you will need to know in Unit 6. So will it have been good to have heard the terms before? Yes. Okay. So this is actually Unit 6 stuff. Okay. The anode, the cathode. But you do need to know that ions move in solution, and that's what conducts electricity. Now, can you please tell me what kind of compounds conduct electricity? So there's 3 types. What's one type? Don't acids conduct electricity? Yes, they do. We just went over that in our last unit, yes? See how we know stuff already? It's kind of nice. Acids. What else conducts electricity? Bases. And what else? Ionic compounds, which are also known as salts. Okay, so who conducts? Acids conduct, bases conduct, and salts conduct. This unit is more concerned about salts than about acids and bases, okay? Okay, so here we have some examples on our next page. How do you know that you have a salt? What kind of a compound is a salt? It is an ionic compound. What do ionic compounds start with? A cation, and the cation could be what? Metal. Or what else? Ammonium. NH4 plus. Ammonium. So if you have a list of compounds and it has a metal at the beginning or it has NH4 at the beginning, you know that it will be an electrolyte. Okay, so you know if something starts with a metal or NH4, it is an electrolyte. Okay. Electrolytes can also be dissolved. Acids. Now, technically, acids are classified as molecular compounds because they're all nonmetals. However, they do dissociate into ions in solution. We just spent a whole unit looking at ions dissociating in solution. How do you know that you have an acid? Starts with H or... yes, starts with H or ends in COOH. Excuse me. So basically, if you want to know, do I have an electrolyte? It's always going to start with a metal or NH4 or hydrogen or COOH. Is that an electrolyte?
Is that not also an acid? So they're not, yes.
Does it start with a metal? Does it start with NH4?
Oh, no.
Does it start with H?
No.
Does it end in COOH? Is it an electrolyte? No. How about this one? I'm just going to write these down because there's people who, you know, are away and will need to see this. So the compounds that we were looking at were 6H12, O, 6, and CH3OH. All right, how about CH3OH? Is that an electrolyte?
Would that be what? Yes, because it's channel we just said maybe
Does it start with a metal? No. Does it start with NH4?
No.
Does it start with H?
No.
Does it end in COOH? Is it an electrolyte? No. Is that a base?
No.
I love that. No?
I mean, is it?
I mean, is it? Is it? Or
OH, no.
it has an OH, but it's not a base. What other kind of compounds have OH that are not bases? Alcohols. This is an alcohol, not a base. Right? And that's why I always go with the rule, does it start with a metal or NH4, or is it an acid? If it doesn't start with a metal or NH4 and it's not an acid, then it is not. Because if you look at all of your bases, NaOH, what does it start with? It starts with a metal, CaOH2. What does it start with? It starts with a metal, NH4OH. What does it start with? NH4.
Oh, ammonium.
Ammonium, okay? So all of those are electrolytes because they do start with those things, okay? Okay, so can a solid salt, NaCl solid, does it conduct electricity? No. Why not? What's not moving?
The ions.
The ions can't move. Yeah, they're stuck in place. Woo! You guys can't read it that small? What's wrong with you? Oh my God. Okay. So the ions cannot move, but the moment we throw this thing into the water, what are the ions able to do now? Move wherever they want to, really, you know? Okay? So in the absence of an electric field, they just move about randomly. If you put them in an electric field, the cations move towards the, what did we call it? Cathode. And the anions move towards the anode. Excellent. And you guys know how to write a dissociation equation, do you? Okay, NaCl solid goes to Na plus aqueous, Cl minus aqueous. Don't forget your charges, okay? All right, next page, aqueous acids. So HCl, before it is dissolved in water, is actually a gas. It does not have strong enough intermolecular forces. What are intermolecular forces? They're forces that do what? Hold molecules together. Do you mean hold the molecules, like, do you mean hold one HCl together, or do you mean hold them like to each other? Ah, good question. Okay, so intermolecular forces are forces between and this is an important prefix, inter means between. If you go on a flight between nations, so say you travel from Canada to Japan, okay, what kind of a flight is that? International, because it goes between Canada and Japan. Thank you. Would you like to look at your test? Are you good till Monday?
Yeah.
Okay, sounds good. You too. Thank you. Did it work? Excellent. Okay. So they're the forces between molecules. And HCl molecules do not have strong intermolecular forces, so they tend to be gases at room temperature because they don't really have very strong forces holding them together. But when we dump them into the water, what happens? They dissociate into ions, so just the same as the ionic compound. We started with a gas, and now we have our positive ion, which is aqueous, and our negative ion, which is also aqueous. Now, other than acids, covalent compounds are not electrolytes. So that would be like those examples we had earlier, C6, H12, O6, CH3, OH. They do not dissociate in water. Instead, the particles simply disperse, which just means they spread out and mix with the water. Okay? So if we look at some solid iodine, I2, we have an I molecule and it is stuck to another I molecule, or sorry, an I atom stuck to another I atom makes an I2 molecule. What kind of bond or force is happening between those two I's? That is a covalent bond. Are covalent bonds strong or weak? They are strong. Can water break a covalent bond? No. However, what's happening in between one I molecule and a neighboring I molecule? What kind of force or interaction or bond is that? That is an intermolecular force. Which is an IMF. Okay, because we get tired of writing intermolecular force all the time. Are intermolecular forces strong or are they weak? They are weak. So they can be broken. Now, it's also going to depend on if you're using water as a solvent. Water is polar, so it tends to break apart other polar molecules from each other. Iodine is not polar, but it's a big enough molecule with a big enough electron cloud that sometimes most of the electrons end up on one side, and it makes a temporary polar molecule. Don't worry about the details of that. You don't need to know any of them for grade 12, okay? All you need to know is that water can break the IMFs in, say, iodine, and so water is there, iodine is floating around, okay? And we have, but all the I2s are still intact. They don't split apart. So we started with I2, and we finished with I2. They're just mixed now. Are there any charged particles?
No.
No charged particles. Therefore, is this an electrolyte?
Yeah.
No. And so really the only thing that changes when you have something covalent is that it changes its state. It changes from being usually solid or liquid or something like that, and it just becomes aqueous when it mixes with the water, okay? All right, therefore all covalent or molecular solutes are non-electrolytes. Except acids, because acids are weird. They dissociate into ions, but you already know that. Yes? Okay. Pure water, also a non-electrolyte. Do you remember when I put the beaker of water onto the conductivity apparatus? What happened? It was super exciting, right? Blown away. Now, the reason is that although water has a positive end and a negative end, what happens is if we have a battery and we have our negative plate over here and we have our positive plate over on the right-hand side, what that means is that half of the water molecule is going to be pulled towards the negative plate. But what's happening to the other half of the molecule? It's being pulled towards the positive plate. And if you take a particle and you pull on one side, but you also pull on the other side in the opposite direction, what does it do? Nothing. Okay? It will align itself like that. It won't be like, wandering around, at least not too much. It'll align itself, but it won't move. Now, are we interested in watching another video of the conductivity apparatus? I sort of have it in here in case we do Unit 3 first, and in case, you're stuck at home and you need to, watch that. Anyone want to see it? We're good? Okay. Do we want to see the dissolving of solid sugar? Yes? Okay, let's watch the dissolving of solid sugar. Ugh. Mouse. Come here. Okay, here we go. Okay, this one has no sound. Okay, so when sugar is added to the water molecules surround the sugar crystals. Now, water molecules are polar, yes? They have a positive end and a negative end. Sugar molecules are also polar. They have positive regions and negative regions. So the water molecules can surround them. All right, due to the strong attraction between the polar water molecules and the polar sugar molecules, the water molecules are able to pull the outer sugar molecules away from the sugar crystal. Does that make sense? So like the little positives on the water, they go over and they grab a negative part of the sugar molecule, and then the little negative part goes and aligns itself with a positive part of the sugar molecule, and all the water molecules surround it and they pull it away. Tyler DeWitt actually has a great video on this if you're interested, but it's kind of long, so we're not going to watch it today. As the outer layer of sugar molecules are pulled away, guess what? The inner molecules are now open to the water. That surface has been exposed, and they can now be pulled away by other water molecules. Is good? And you watch, they just disperse. Okay? All those little sugar molecules are just dispersing, but are they breaking apart? No, the individual sugar molecules stay intact. And that's all there is to that. Okay? There's just no more room. Yeah, basically. Yeah, and it just depends on, there's other things it depends upon, but let's not go into that right now. Okay. Now, what else do we have here? Let's check and see. We have dissolving of solid sugar. This link I need to get rid of because it's dead now. It's a dead link, so we can't watch that. Would you like to watch dissolving of salt?
Sure.
Yes. This one's actually quite nice. It actually has words along with it.
Imagine.
Okay, we don't want to watch that.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
And that's that. Simple little video, but do you see how it works? The positives grab the negative and pull it away. The negatives grab the positive and pull it away. And it works the same with sugar, except for sugar has bits on it. It has little bits that are negative here, here, and here, and it has little bits that are positive here, here, and here because it's a bigger molecule. And so the waters will align themselves in the direction that they need to in order to pull that sugar molecule away. Okay, what do we got here? Movement of sodium and chloride ions in water. So this is going to show what happens when we have those ions moving.
How to get... Imagine you can see the charged particles in solution. There are sodium ions, which are positive, and chloride ions, which are negative. The others are present in water. Positive hydrogen ions and negative hydrogen.
How many positive hydrogen ions and negative hydroxide ions are there in water? Lots?
Oh, wait, no, not. So repeat the question.
How many hydrogen and hydroxide ions are there in water? Ions. Not none, but very, very few. In fact, you could give me an actual number if you thought about it a little bit. Think about it a little bit. See if you can actually give me a number.
Oh, we'll put for times 10 to the negative 14.
Not times 10 to the negative 14. 1 times 10 to the negative 7 molar. Yes, pH is 7. So the concentration of hydrogen is 1 times 10 to the negative 7. Yes.
Hydroxide ions. These
But they're still
different
there.
charged particles are all free to move. Once the power supply is switched on, the positive ions are attracted to the negative electrode. The negative ions move towards the positive.
All right. What do we call the electrode on the left?
Cathode.
Cathode. How do you know that?
Because cations are attracted to the
That's where the cations went. What do we call the electrode on the right? Anode. Why? How do we know that? That's where the anions went. Okay, cool. And let's see if there's anything else useful on there. I think that's it. Yeah. Okay, so we're going to skip on to 3.1b. I'm going to let you do that over the weekend. So, ionic and molecular solutions, you are going to do this on your own. Now, when you do it on your own, do you see what I've put here with stars? Read the boxes. There's not actually any new information on this sheet, but it's just a review of how to write dissociation, how to write dispersion, how to recognize ionic and molecular substances, okay? Do as much of this as you need to feel like you understand it. So if you're feeling good about it, you might be like, I'm going to do column number 1, and if I feel really good about column number 1 and I got them all correct, maybe I don't need to do column number 2. But if I got some wrong, maybe I'll do column number 2. Does that make sense? Okay? Because I don't want to make work for you, but also, I would like you to be very good at this. For example, can you point out an alcohol on here? Can you guys see an alcohol? Any alcohols? CH3OH is an alcohol. Is it going to conduct electricity? No. All right. So there's a bunch of things. Recognizing acids, writing dissociations, writing dispersions, recognizing electrolytes and non-electrolytes. You know, just do every other question or whatever. And now, precipitation reactions. Do you remember seeing these before at the beginning of semester? Yes. Okay, good. So let's remind ourselves of the word precipitate. The precipitate is the solid that forms in a double replacement reaction when we mix two aqueous ionic solutions. And you can change the word precipitate and write it simply as PPT. Okay, there is a helpful video here, so if you don't remember how and you're trying to do the questions over the weekend, you can be like, okay, I'm going to watch that helpful video. But we're not going to watch it right now. We're going to look at this reaction. We have sodium chloride, aqueous. Sodium chloride is a soluble salt. If you didn't know that sodium chloride was a soluble salt, where could you look? You could look on the solubility table, which is on page 4 of your data booklet. So for example, here we have, look, sodium is an alkali ion. And what are alkali ions soluble with? Everything. So anytime you see sodium, you know it's soluble with everything. Every time you see potassium, it is soluble with everything. And I've kind of scribbled over lithium, poor little lithium, but lithium is also soluble with everything. So if you have those in a salt, it will be soluble. Okay. AgNO3 is also a soluble salt. And once again, if we go to our data pages, how do we know it's soluble? Nitrate is another one. NO3 is soluble with everything. So if you see nitrate in a salt, it will dissolve. Okay? Oh, wrong one. There we go. So, do you remember how to predict the products of these reactions? You combine the inside and outside ions. So if we combine our outside ions, we have Na plus and NO3 minus, which gives us NaNO3. Will NaNO3 be soluble or low solubility? Soluble, because guess what? We have an alkali ion and we have nitrate. And nitrate is soluble with everything. Okay? Okay. What's happening here? Okay. Are you going to work for me? You are. Bless you. No, you're not. How come you'll write sometimes and you won't other times? What is wrong with you? Let's see if we can make this thing work just a little longer. Okay. Whew. So now we combine our inside ions, and remember the cation still has to go first, so we have Ag and Cl. And please go look on your data table and tell me whether AgCl is going to be soluble or low solubility. Page 4.
CL.
Cl.
Okay, I'm guessing it is soluble. Oh, wait, it's not. But you're right. Is it a water with it? No.
Do you want me to sing the Jeopardy theme song? Would that be helpful? Da, da, da. Okay. Chloride with silver is
Non-soluble.
low solubility. And if it is low solubility, what does that mean? It is a
Precipitate.
solid. It is a precipitate. Okay? So that's going to look like this. So we have NaNO3, which is aqueous, and we have AgCl, which is the solid. Here is our precipitate. And you can see the Na and the NO3 are still floating around. Could you write the complete ionic equation for this reaction?
I think I remember that.
You think you remember it? You write a complete ionic reaction by separating the ions of the aqueous compounds. Give that a try. Now, if you're copying me, you're not thinking about it. So try and think it through on your own. But when you are done, feel free to look at what I've written and think, has Miss Spence done a good job or a poor job?
Oh. And like, I wasn't copying. In that case, I wasn't copying. Let's have me both thinking on my own.
Isaiah, I love having you in this class. It's amazing. It's like I'm always guaranteed some positive interaction, right? Like if any of the rest of you want me to be like, I love having you in this class, you just start talking to me and I'll be like, or start answering questions out loud and I'll be like, oh my God, I love having you in this class. Anyway, I love having all of you in this class. I do. You're all very special people, but the more you talk to me, the better I feel. So there we go. Anywho, have I done a good job or have I done a poor job? I have done a poor job. What have I done wrong? Oh, I repeated Cl. That was one thing that was wrong. Yeah, that's a bad one. Didn't even realize I'd done that one. That was just me being me. I need my states and my charges. States, charges. Who are our spectator ions? Na plus, because it has stayed the same from one side to the other side, and NO3. Excellent. So if you would like to now please write the net ionic equation. So we had spectator ions were Na plus and NO3 minus. Would it be okay to write the Cl first and the Ag second in the reactants? Yeah, that would be fine. I have a tendency to always put my cation first just because it looks nicer to me, but it would be okay to do it the other way. No problem. Okay? Now, just so you know, you could actually go straight from somebody saying to you, you have AgNO3 aqueous plus NaCl aqueous. Please write the net ionic equation. And if you can say to yourself, oh, that's going to be aqueous, NaNO3. AgCl is going to be my solid. You can say, oh, I'm just going to put AgCl as my product. And what do I need to make that product? I need an Ag and I need a Cl. So you can kind of skip all those intermediate steps if you are just asked to find the net ionic equation. Okay? So you don't have to always go through the process of complete ionic, net ionic, unless you're asked to write the complete ionic, net ionic. Okay? But you can go straight to the net if you want to. If it makes sense. If not, do the complete ionic and then go to net ionic. Doesn't matter. Now, we have 5 minutes left and we have 2 special cases. Because look what we have here. We have 2 precipitates. When I take my copper 2+ and my OH-, if I look that up, data pages, hydroxide, copper is not up here. It's not an alkali metal. It's none of the other ones. So Cu 2+ is here. So it's going to form a solid. CuOH2 solid. Strontium. When it gets together with sulfate, once again, we could look on our table. Wrong table. Sulfate. Sulfate. Come back here. Where are you? Sulfate and strontium is low solubility. So once again, that's going to also be a solid. You guys know your phones make you stupider, right? Just saying. What happened? Where am I? Here we go. So strontium gets together with sulfate and it forms a solid. So let's write the complete ionic equation and net ionic equation for this reaction. Split apart your aqueuses and leave your solids together. Everybody write your complete ionic equation. And once you've written your complete ionic equation, you can look at mine and critique mine, because mine always needs critiquing, doesn't it? Shouldn't it be OH minus? Yes, it should be OH minus. Yes, we need that there. Good. Oh, I need brackets where? CuOH, like that. And I need a 2 because copper 2 plus needs 2 OH negatives. Have I missed anything else? Don't I need a 2 coefficient in front of the OH? Indeed I do. I needed all of those things. Good job. Now my net ionic equation. What do I do? It should be the same because there are no spectator ions. And our last case, no precipitate. Well, if we take a look at our ions, we can see that we have Na. Na is an alkali. What do we know about all alkalis? Alkali salts. They are all soluble. So when I put Na with S, that is going to be aqueous, yes? Now, K, is K an alkali?
Yeah.
Yes, K is an alkali. So when I put it together with NO3, it is aqueous. And if we look, all my ions were all floating around. And now what are they doing after the reaction? They're still floating around. They're just all in the same beaker now. So what is my complete ionic equation and net ionic equation? There is no reaction. Nothing happens. So you can just write NR. Okay? NR. And over the weekend, you're going to do 3.1a, 3.1b, 3.1c, as much as you need to feel like you have reviewed those to your satisfaction. Okay?